Okay, there we go. So I'm starting to record. So yeah, last time we finished up talking about that binary search thing, right? We were talking about binary search, and then we also spent some time talking about how certain programming languages are very similar and other programming languages seem quite different. And like we saw, Python, C++, and Java they were all quite similar, especially Java and C++. They were very similar. But even then, the algorithm itself was the same. Like if I were to take that algorithm and kind of turn it into what we call like pseudocode, and I would like explain like the English or whatever language of what each line of code does, like for each element, you know, like instead of writing the code for the for loop, if I were to like explain it in English, it would be the same for all those languages. The code is the same, but with Haskell, it looks quite different. And we also got a chance to look at recursion a little bit, which was fun with Haskell. So today I am going to start, nope, that's not what I want. I'm going to start sharing the screen, share. Ooh, there we go. So here we go. We're going to talk about some sorting algorithms. Now, I want to be very clear, and again, this isn't going to be on the exam, so don't worry about this. Worry about it to the point where we can get the intuition of how these sorting algorithms work. I want to be clear, though, sorting algorithms, despite the fact that I know every single person in this room right now, or this room, have sorted things in your life, whether it was things alphabetically, whether it was by size, by color, whatever, you've sorted things. I know you have. And when sorting those things, you followed some sort of algorithm. Chances are it was a mishmash of different algorithms for sorting things, but you've all sorted things before. But despite that, in computer science, we like to start, once we want to like sink our teeth into like algorithms, we always like to start with sorting. We like to start with sorting because we all know what sorting is. We've all done it, but it's surprising how funny it is to kind of formalize sorts. It's funny, but it's funny when we formalize these sorting algorithms and you get a chance to look at it formally, despite the fact that you've been doing this for years. And yeah, so we like sorting algorithms, and sorting algorithms also give us a chance to do some like geeky computer science stuff where we ask the question like, well, how much work is this here? Anyways, so sorting. I mean, we can't really do this because everyone is like, we're on Blackboard Collaborate, but chances are you all sorted something in your life. Great. Now, again, another warning. Before we start looking at these algorithms, it's important to note that none of these algorithms, the implementation of these algorithms is not what's important. It's the high-level idea, the main mechanism in how the sorting algorithm works that makes these sorting algorithms the type of sorting algorithm they are, not the specific code or implementation. Because each of these algorithms, even in Python, I could code up a bajillion different ways, and they'll all work the same way-ish, but the code can look very different. So it's not the implementation that matters, it's the high-level idea that matters. So here's the idea of insertion sort, and I'm willing to bet you've kind of used this before. I know I have. If I give you a list of things, call it in list, right? And here's what I'll do, is I'll create a new empty list. And then what I'll do is, for each element in list, I'm going to insert that element into the, starting sorted list in the correct spot. So, for example, if I'm asked to insert 5 into the list 137, I should end up with 1357, because I would take 5, look at the 1, and be like, well, does 5 go before or after the 1? Well, it must come after. Does 5 go before or after the 3? Must come after. Does 5 go before the 7? Oh, yes, it does. So I know it must go between 3 and 7. Great. That's the idea. And we can do insertion sort here with pencil, paper, or a whiteboard, and let's see how this plays out. So let's stop this and a whiteboard. So I know I started with here. There we go. Here, I know I started. Whoop. That's not what I want. So here, I said start with like something called in list, And we don't even really need to start it with the idea of having an actual list. We could just think of having like a collection of information, like maybe like a bag or something. And I've got some numbers in there. I don't know, maybe I've got 5, I've got 4, 7, 2, 9, 8, 6. There we go. Great, perfect. So these are the numbers we have that we want to sort. So what I'll do is I'll start with my empty list. There's nothing in there, right? Great. And I'm going to randomly pick out one of, let's see if I can change the color here. How do I change my color? Red. I'm going to randomly pick one of these numbers. It doesn't really matter which one. Assuming we're using like with in-list, we can, I mean, the list will be ordered. But if we're using a bag, it doesn't really matter which one we start with. So let's pull out 6. So 6 is gone. And then what I'm going to do is I'm going to take the number 6, and that's my list. Let's see how good my trackpad drawing is. Okay, great. I mean, when an empty list is sorted, and so, but there's nothing in there. So I guess like, oh, what? Who did that? I think I did that by accident. Can I undo? No, undo. Darn. Well, let's try that again. Still learning this, so let's see. Okay, we've got our, whoop. It's this bag of numbers. I'll just draw it now. We've got 6, 4, 2, 7, 8, 9, 5, 1, 3. Great, those are our numbers. Now let's change the color to blue. So we start with an empty list. And it doesn't matter what number I start with. Let's go with 6 again. That number I can just put straight into the list, right? Because I know that that list with only one thing in it is still going to be sorted. So there we go. There's the 6. Fantastic. Great. I still have a sorted list. And just bear with me. That is the number 6. Okay. Now, let's pick another number. 8. Okay. So I have to ask the question now, like how should we write this algorithm? I mean, we know, like if I look at this, I mean, you immediately know, well, the 8 comes after the 6, but you got to think, okay, well, how is the algorithm going to look at this? You know, we're probably going to use a for loop, and we're going to look at each thing. And here's what we can do. We can simplify that previous example I was just talking about like, oh, does it come before, after, before, after, before, after, by just asking a single question. We look at a given element, and we ask the question, does this number come before this element? So I can look at 6, because that's currently the list, and I ask the question, okay, does 8 come before 6? And the answer is no. So I would go to the next thing. Now, we're actually out of spots. There's nothing after that. So we know that if 8 doesn't come before 6, it must come after, right? So the list would become 6 followed by an 8. Great. So now we'll pick another one. Let's go with 5. Okay, so let's look at the first number. Does 5 come before 6? Oh, yeah, it does. Okay, great. So that's easy. 5, 6, 8. Cool. So another number, let's go with 7. Okay, so now again, does 7 come before 5? No. Does 7 come before 6? No. So remember, if 7 doesn't come before 6, it must come after 6, right? We know that. I mean, I don't know how far after. You can imagine I'm looking at the number 99. 99, if 99 doesn't come before 6, I know it must come after 6, right? So as soon as I go past a given number, and I've answered the question, does this number go before the number I'm looking at? Does the current number I want to insert go before the current number I'm looking at? If the answer to that is no, it must come after. I know that. So let's start again. So does 7 come before 5? No. Does 7 come before 6? No. Does 7 come before 8? Yes. And because it didn't come before 6, I know it must come after 6, but it also must come before 8, so it just goes right in the middle there. Let's see if I can squish this all into this line here. 5, 6, 7, 8. There we go. Great. Let's add, I don't know, 9. All right, well, does 9 come before 5? No. Let's see if I can just speed this up a little bit. Does 9 come before 6? No. Does 9 come before 7? No. Does 9 come before 8? No. Does 9 come before, oh, I guess we're done. So there, that must be it. Okay, cool. All right, so now let's say, I don't know, we're adding 3. I don't know. So, okay, so does 3 come before 5? Oh yeah, okay, great, done. 5, 3, 5, 6, 7, 8. Okay, great. Then we can add, let's say we're adding 4. So does 4 come before 3? No. Okay, so 3. Does 4 come before 5? Yeah. So I know it must come after 3 and before 5, so there we go. 5, 6, 6, 7, 8. And then we can go here, let's add 1. All right, does 1 come before 3? Yeah, all right. 1, 3, 4, 4, 5, 6, 7, 8. Okay, let's add the 2 because it's the only thing left. And we end up with, does 2 come before 1? No. All right, so we start with the 1. Does 2 come before 3? Yeah, all right, 2, 3, 4, 5, 6, 7, 8. Great, done, we're sorted. Fantastic. We can look at the code. Let's clear this and I suppose go back to this. So if we go back and look at the code here. So here I was saying that, you know, as a good exercise, you could do this on pencil paper, kind of like what we just did. But we can look at this code here. Here's some code for a given implementation of insertion sort in Python. So we start with inList. That's the list of things we want to sort. Sorted list, that's going to be the empty list that we're adding to. Then we ask the question for each element in inList. So we have to look at each element in the inList, the list that we want to sort. And then I've got this going on here. Okay, there's a lot. Well, I is less than the length of sorted list, okay? And element, which is the thing I'm looking for, is greater than sorted list at I. Oh, interesting. So now it's saying if element is greater than sorted list at I. Huh. Well, this is actually interesting because it looks like this implementation actually switched the less than and greater to, or less than and greater than. But I mean, it doesn't really matter. It's arbitrary. Again, any implementation will work just fine. So we figured, you know, if the length of the list starts at 0, well, I is less than that, you know, it's going to keep looping. We just keep adding 1 to I. So we keep saying, okay, is I less than the length of the list? If it is, and the element is bigger than sorted list, keep going, keep adding 1. And we're going to go until either we get to the end of the list or the element is not greater than sorted list at I. Great. And we're going to keep doing that, and we're going to find I. So I will stop because we're going to stop looping. I is going to stop at the proper index of where it should go. And then we just say, okay, sorted list.insert at location I, the element. And keep doing this over and over and over again. And then at the end, return sorted list. Fantastic. So I'm going to take this so we can do that next activity together. I'm going to take this code. So great. And then I'm going to change it a little bit. So for each time, print sorted list. So each time through the loop, we're going to print what the sorted list is. And I'll call insertion sort with, I don't know, 5, 2, 8, 4, 1, 7, 9, 4, 5, 7. I don't know, whatever. It doesn't matter if there's duplicates or not. Let's see what happens. Okay, great. So we add the 5, yeah, and then 2, okay, and then the 8, okay. And then, I mean, it checks out, right? Like it does the trick. So that's cool. And we can see like how at each step, based on the ordering of these things, how those numbers got added. Like, I mean, if I change the 9 to a 6, we'll obviously see the 9 disappear, and then there'll be a 6 between the 5 and the 7. I guess there'll actually be 2 6s. Yeah, there we go, 2 6s. Fantastic. Are there any questions so far about, so let me know if there are any questions about the insertion sort at this stage. It's not a crazy algorithm, but it can be kind of funny to start talking about sorting algorithms when we haven't quite done it yet. So just raise your hand if you have a question, or just type the question in the chat. I'll give you a second. All right, then I'll assume we're all okay. So let me go back to sharing. Okay, so now, can you see? Okay, yes. Now we want to get geeky about this. We want to be computer science nerds and think about the question, how much work does this code have to do in the worst case scenario? I mean, when we're looking at linear search, we knew that like the amount of work we had to do was linearly proportional to the size of like the list we were searching through. So if the list was size 10, worst case scenario, we'd have to look at 10 things. If it was size 20, 20 things. If it was size n, n things. Great. I wonder if we can kind of do the same thing. I mean, and we did that yesterday too with binary search, right? Because binary search, we saw that it wasn't linear. You know, it had that logarithmic relationship, log base 2, which was really cool. And that's way better than linear, so we like that. So I'm curious how much work insertion sort is in relation to how big the list that we're sorting is. How much work is it? So let's have a look at this code. Actually, maybe we'll just look at the code here. Have a look at this code, and I'm going to give you a minute. I'll give you until 1:36 to look at this code here and try to figure out the worst case scenario. First, try to figure out what the worst case scenario is in terms of what the list must look like, and then how much work the code is doing in proportion to the size of that list. Now, I'll give you until 1:37 actually, because it rolled over. So I want to give you a little bit of time to think about this and really think about it, because this right here is one of the fundamental important questions and things we look at in computer science is how much work is this code doing? So take a moment, think about this, and see if you can come up with an idea of how much work it is and whatnot. While we're waiting, maybe raise your hand if you think you have the idea. You don't have to be like right or anything. You don't have to be that confident. I just want to see if you can, like, how many people kind of have an idea before we talk about it. You leave the hand up. Okay, so let's talk about this a little bit. Now, I'm going to cheat a little bit. This isn't always correct. This isn't a silver bullet, but a lot of times when you see nested for loops, or pardon me, nested loops, where one loop is inside the other loop and they're both like going over the length of something, see how like element in list, so that means it's going to look at each thing in the list. And then we're also seeing I, well, I is less than the length of the sorted list, and that might go to the full length of whatever in list is and whatnot. Whenever you see lists inside of each other, a lot of times we like to think n squared. So let's slow down and think about this. It might help by starting to think what the worst case scenario is. Not how much work relative to n, but what is true about in list that will make this work particularly slowly. First things first, this outside loop, it has to run for each thing in the list, right? So this list, all the code, this for loop here, all the code inside of it must run at least n times. So now the question we have to ask is, how much work is there taking place inside that loop? And whenever you see a loop, that's where things kind of get hairy. We have to go, oh, okay, so what's going on? So this outside loop must run n times, whatever n is the size of that list. So there's nothing really much about that there. But so the question we're asking, well, I is less than the length of the sorted list, or if element is greater than sorted list. How can we make this loop, like in the worst case scenario, how can we make this loop run the most amount of times? Because worst case scenario, we want this loop, like all the code to be running as much as possible in the worst case scenario. And then after we do this, we can talk about the best case scenario. But we ask the question, okay, is I less than the length of the sorted list? So let's say the length of the sorted list is some arbitrary value k. Let's not worry about what it is, but it's k. And is I less than k? Let's say it is. Then we have to ask, is element greater than sorted list? Okay, so if element's greater than sorted list, it'll run again. So if I is less than k and the element is bigger than the current thing I'm looking at, then I'm going to run this loop again. And all this loop does is count. So I need to make sure that each element coming in is bigger than, I guess, everything in the list so far. So I think the worst case scenario might be if we start with the list and we start with the in list being the list is already sorted in reverse order. I think that might be the trick. So let's have a look over here. So 9, 8, 7, 6, 5, 4, 3, 2, 1. So it's going to be hard to see how much work is being done here, because we're only printing out something inside this loop. So we're going to want to probably print out what I is or something as well. But first of all, I mean, we can count how many times this is printed out, and that'll tell us how many times this loop ran. This is size 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, 1? Oh yeah, because we start with the empty list. Gotcha. Okie dokie. So how can we see how much work is going on here? Well, you know what? I think what we can do is do like print I. Let's see what happens. Huh? Oh, or did I do it backwards? I probably did it backwards. Someone has a comment here. Wouldn't it take more steps if the opposite was already in order? I think you're right. Look at that. Looks like I probably got mixed up because of this less than greater than thing here. So actually, it looks like this while loop never ran because I'm not printing out I. So why did it never run? So let's see. We get 9. we go in, so we're looking at line, is I less than the length of the list? No, 0 is not less than 0, so we just add it at 0. Okay, great. Then we're looking at 8. Is 0 less than the length? Yeah. Is element greater than? Yes, it is. Oh, okay, so it looks like, wait, if I is 0, how on earth? So I is 0, we start over, we're looking at 8, 0, 0 is less than 1. Is element 8 greater than sorted? Oh no, it's not greater than. So 8 is not bigger than the element at sorted list. My goodness, how am I messing up so much today? So because that's not the case, we don't run this loop and we just insert at the beginning. So it looks like every single time we're inserting at 0. Yeah, that makes sense. I mean, we could even see it going on right there. Okay, so it looks like this is actually the best case scenario. Okay, so we'll come back to this in a moment. In fact, let's just do this. So it looks like it's probably the opposite. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ah, okay, look at this. This is more telling. So first, okay, let's rerun it here. Here, let's do that. So we're not printing up the numbers yet. And we can see that this runs 1, 2, 3, 4, 5, 6, 7, 8, 9. And then, okay, good. And the last thing, yeah, okay. And now let's add this back in. So the first time through the loop, okay, nothing, that loop doesn't run. But then we see that this actually does get to 1. Then it gets to 2. And then 1, 2, 3. 1, 2, 3, 4. So it looks like the fourth time through that loop, we're actually running up to 4. So on the fourth time through, it's running 4 times. Fifth, 5 times. Sixth, 6 times. 7, 7 times. 8, 8 times. 9. Well, I guess the last time we're just doing that so we don't see it. So I'm curious. Oh, actually, no, we're not seeing it because we didn't print it out, I think, before. But anyways, so what's, like, how much work is this? Well, it looks like that loop is going to, like, okay, so that first time through the loop, let's go back here for a second and switch this to a blackboard or whiteboard. So the first time through that list, okay, we know that list is going to run, or that loop, that outside loop is going to run n times. But the first time, it looks like the loop run like once. And then the next time, it ran 2 times. And then 3 times. So this is how much time the inside loop is running. Then it ran 4 times. And then dot, dot, dot. Then it ran like n minus 1 times. And then n times. Let's just add brackets there so it's obvious. And here, let's see if I can do this. There's n things here. So the first time through the loop, okay, 1, and then the next time 2, the next time 3, the next time 4, da, 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 then n minus 1, then n times. So the last time through the loop, the inside loop is going to run n times. So the outside loop we know is running n times. So for each of those n times, how much work is being done? Well, the first time it's 1, then the next time it's 2, then the next time it's 3, the next time it's 4. Let me ask you something. How many people recognize this, what we're looking at right here? Raise your hand if you recognize what we're seeing here. Oh, Trent lowered his hand. Oh, a couple people raised their hand. Someone type it in the chat. What do we see? What do we see interesting about this series of numbers? Oh, come on. Someone type it in the chat. Exclamation point. Nope, not factorial. That would be like multiplication, but so okay, let me take a step back. Let's think about this actually. Because you're right, this could be confused with factorial because I didn't do anything. So I want to know how much the total amount of work is here. So the first time through the loop, it's one thing. And then we're going to have to add all these things together, actually. to know the total amount of work. So 1 plus 2 plus 3 plus 4 plus plus n minus 1 plus n. Great. There. So like we're actually adding all these things together to know what the total amount of work our code is doing. No, not exponential, summation. So this looks to me like an arithmetic series, right? And I know we've all looked at this back in high school, but it's probably been a little while. Does anyone remember the formula for arithmetic series to figure out like very quickly what the formula was? And I think there's like a little story that goes along with it. I don't know how true it is, but I think it was like Euler, right? And it was like, yeah, there you go. Who wrote that? Trent. Absolutely correct. N times n plus 1, or is it n minus 1? Yeah, n plus 1, I think. And divided by 2. Great. Raise your hand if you recognize what Trent just wrote. Okay, a bunch of people. That's good. So you probably did learn this in your high school, but it's been a while. And the trouble is, there's a good chance you're actually taught this in a very poor way. But let me explain why it's n times n plus 1 divided by 2. I'm going to show you an easy way to derive this. If you ever forget this formula there, we can derive this really easily. Because here's the thing. Here's what we can do. I could, let's say, just go with me on this. For some reason, I'm going to double the input here. Okay? So I'm going to, I don't know, pick the number, the color's orange. Okay? And I'm going to do this. 1 plus 2 plus 3 plus 4 plus plus n minus 1. I need to get myself one of those like bamboo track pads or something. There, great. So if I add all these together and then like, I don't know, 1 plus 2 plus 3 plus 4 plus n minus 1 plus n plus n minus 1 plus blah, 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 then I'll have twice as much of what we're supposed to have. And if at this stage you're thinking like, okay, what? Let me do this. I'm going to rewrite this actually a little bit different. I'm going to take this and just write it in a different order. N plus n minus 1 plus ... I guess we can only have like 2 plus 1. So I want to add all these things together. And I mean, when I do addition, the order doesn't really matter in which way I do the addition, right? Like I can do 1 plus 2 plus 3, or 1 plus 4 plus 2 plus n minus 1 plus n plus 3 plus, and so on. Like the order doesn't matter. So what if I do 1 plus n? Well, I mean, 1 plus n is n plus 1, right? And then what's 2 plus n minus 1? Oh, well, that's just n minus 1. Now imagine I had n minus 2 plus 3. Well, that's n plus 1. Or why did I write minus? Plus n plus 1. And then I go What's n minus 1 plus 2? Oh, that's just n plus 1. And then what's n plus 1? Well, it's just n plus 1. I guess I need to write my addition. N plus 1. Great. So now I have a whole bunch of n plus 1s. And let me ask you, someone type in the chat, how many n plus 1s do we have? I'll give you a hint. Half of n. No, not half of n. N. We have n plus 1s because we have n here. And then we did that again. So now we have n. So you know what? This is just n times, okay, let's actually do like times n plus 1. But of course, this isn't the answer, right? Because I added a whole other series of the numbers of 1 through n. Like I just doubled 1 plus 2 plus 3 plus 4, n minus 1 plus n plus 1 plus 2 plus 3 plus 4, n minus 1 plus n. So like I added this series twice. So I need to undo that doubling. Any idea on how I undo a doubling? Well, that's easy. You just divide by 2. Huzzah! There we go. Look at that. Now, this is a bit, and this, by the way, is what Trent had written for us. Now, we look at this and go, okay, so the total amount of work in there is n times n plus 1 divided by 2. Whenever we look at like the worst case scenario and how much work is being done, we often like to ignore coefficients on the the size of n. Let me rewrite. First, I'm going to write this as 1/2 times n squared plus n. Right? That's the same thing, right? So whenever we're looking at the worst case scenario, I'm just going to ignore this half. It doesn't really change it in terms of how much worse this algorithm gets as we increase the size of n. Because the thing that really dictates how bad this code grows is the thing with the highest exponent. And even this n part here doesn't really matter so much, because the growth of n, as n grows, is linear. Where the growth of this, it's quadratic. So this is like getting way bigger, way faster. Like if n is 100, this is going to be 100. But then we've got 100 squared. That's way bigger than just 100. So long story short, we look at this and we go, oh, it's n squared. So the total amount of work in this worst case scenario is n squared. This is a lot worse than our linear search, right? Linear search was order n. And then we've got our binary search, which is way better than n squared. But I guess n squared isn't too bad, right? I mean, it makes sense that we're going to have to look at everything a couple of times, because this is basically saying I'm going to do n amount of work n times n squared. And that kind of makes sense because we've got this loop and then the other side of the loop, and that might go to the end of the list every time. So we're going to do n things n times. So n times the n, kind of. So as n grows, this is going to get a lot slower. But also, I suppose it doesn't feel that bad, because if we're doing sorting, we need to keep looking at other things to know where to insert the things. Okay. Now, we also talked about that worst case scenario, or the best case scenario. And this is basically where we just keep adding something to the beginning of the list every time. And in this situation, let's think about the total amount of work. Well, we know this outside loop is going to run n times. So how much work is being done each time this loop runs? Well, because element is never going to be bigger, based on this ordering, is never going to be bigger than the thing I'm looking at, we see that, oh, I just got an emergency test. This is a test of the National Public Alerting System by Nova Scotia. This is only a test. Did anyone else get this, or am I crazy? No one else got it? Yeah, okay, you got it. All right. So I saw that and thought, uh-oh, what's going on? But it's just a test, so that's good. Okay, back to learning. So because element is always going to be we added 9, great. Then we're adding 8. 8 isn't bigger than sorted at I. So we don't actually have to run this loop. And this loop here is never actually gonna run when we got this ordering, meaning that the amount of work this code is doing is I don't know, 1, 2, 3, 4, 5, 6 lines of code, and that, I don't know, there's not that much work going on there. So, oh my, a lot going on upstairs. 1, 2, 3. This is all like constant time work, meaning that, I mean, it doesn't depend on the size of n. So we're doing constant work n times. And whenever we're doing constant work, it doesn't really matter. We don't consider like, oh, it's 5 lines of code versus 1 line of code and it's all constant time. Like we only say like, okay, it's constant. So we're doing the same amount of work every time through this loop, meaning that here in this best case scenario, the amount of work is linear. Huh, okay. So that's insertion sort. But like, okay, here, quick, raise your hand. Oh my goodness, I haven't been sharing my screen this whole time, have I? Why didn't anyone say anything? Oh no. Or have you been able to see my screen when I was typing the code? Or are you just stuck looking at the whiteboard? I can see the whiteboard. Oh no. Well, I just talked, only able to see whiteboard. Why? Okay, you gotta say something. I'm still getting used to teaching on Collaborate. Okay, let me go over that again then. So, this is what we were looking at. So this is the best case scenario. So we know that this loop has to run n times. So the question we're asking here is, wait, you still can't see, can you? Because I'm not sharing my screen. I swear I'll get better. There we go. There, can you see it now? Not the code, but the infinite. Okay. So now let's try this again. So this outside loop, no matter what, no matter the ordering of this stuff, I have to look at each element in the list. I have to. We can't do better than this. So for each thing in the list, and we know that this is going to run n times where n is the size of in list. Okay, great. So now we ask the question, in this best case scenario, how many times is this, like how much work is being done inside this for loop? And this is constant time, this is constant time, this is constant time. The only thing that might vary is this while loop, right? So this is what was varying last time, is the first time through the loop, this ran like, the 0th time it ran 0. The first time this loop ran once, and the next time it ran twice, and so on and so on and so on. That was in the worst case scenario. But now we're asking the question, okay, so the numbers are coming in reverse order. So 9 is the beginning of the list. And then I ask, okay, is I less than sorted list? Yep, okay, true. Because sorted list length is 1, okay. Then I ask, is 8 greater than 9 in this case? And it's not. So this loop doesn't run. And because each number coming in is smaller and smaller and smaller and smaller and smaller, I don't actually ever run this code because this condition is never true. So this code, like it doesn't loop, meaning that the amount of work this is going to do, it's never going to run. Meaning that the amount of work taking place inside this for loop does not depend on the size of n at all because of this little catch here in this best case scenario. In the worst case scenario, it did depend on n. But in the best case scenario, where they come in reverse order, it does not depend on n. So because it doesn't depend on n, like that's just constant time. So the amount of work being done every time this loop runs is like constant time. So we can kind of like ignore that. And we just ask the question, well, how many times does this loop run? It runs n times, where n is the length of the list. So the amount of work being done in this best case scenario is n, which is way better than n squared. And isn't it kind of funny that the effectiveness and like speed, for lack of a better term, of this algorithm is dependent on kind of like what the input, not just the input size, but kind of like what the input is structured like. Isn't that kind of neat? So raise your hand in the chat if you think maybe sometime in your life that like, you know what, yeah, I've done insertion sort. Like I didn't know it was called insertion sort, but I've definitely done that code before. So, or not code, I've done that algorithm before when sorting something, whether it was like, I don't know, people alphabetically or I don't know, anything else. And I mean, like, of course, there's a lot of people who have probably done this. And we don't have time for it today, but we're going to look at 2 other ones, I guess, on Friday, selection sort and bubble sort, which are 2 other popular ones that are kind of easy to look at. But there's also one more really fun one that I suppose we can look at today called BOGO sort. I'm going to share my screen. Looks like a lot of people are leaving before I'm done, which is too bad, but I'm going to share my screen again. I just jumped down to BOGO sort. I mean, I skipped over selection and bubble, which we will do on Friday, but I want to have a look at BOGO sort. Take a look at this code and try to figure out what it's doing. I'll give you a second, look at it, and try to figure out how it works. Raise your hand if you think you have an idea. A couple people. So let's talk about it. So this function right here, all it does is just checks if a list is sorted. In list, okay, we start at the beginning thing, last is the first element, and then we say for each element in the list starting at, I guess, the thing at location 1, if last is bigger than element, then it must be false. So if a bigger number comes before a smaller number, then the list isn't sorted. And I guess this is just assuming we're sorting in descending order. So like low to high. So all this is doing is it's basically just a linear search. Let me say that again. This is just a linear search, except instead of looking for a specific element, we're looking for any adjacent things out of order. If you find anything out of order, we know it's not sorted. We only know if it's sorted if we get to the end and nothing was out of order, right? So this is just a linear search with a twist. So all this function does is checks, is it sorted? And we have to ask, how much work does this code take? Well, we see, pardon me, we see the one for loop here. So it's, it's just dependent on the size of n. This is going to be order n. Then we go down here. So we see BOGO sort and it takes in list. And it says, well, not is sorted. So if the list is not sorted, shuffle it. And then ask again, and then shuffle it, and then ask again, and shuffle it, and ask again, until we get a sorted list. So does this seem like a good sorting algorithm? I mean, this sorting algorithm is effectively, imagine I gave you a deck of cards and said, oh, are these cards in order? Yes or no? If they are, great. If not, shuffle them and check, are they in order? Yes or no? No, shuffle them, and so on and so on and so on. I mean, if I were to ask you how much work this code is doing, I don't know, quite a bit of work, right? Because I mean, it's possible that I shuffle the deck of cards and every single time I shuffle it, I get the exact same ordering. That's not the right ordering. So, but they found a YouTube video with the BOGO sort. Yeah. So BOGO sort, probably not a great sort, but it's definitely, but it is still a sorting algorithm. It technically might not ever end, but anyways, we'll end there for the day. I'll see you. Remember, no lab tomorrow, although I do encourage you to do the lab, but you don't need to submit it. And otherwise,